All right, let's take a look at the Unit 5 learning targets 1 through 4. So, first learning target is about energy transformations, energy transfers, the different types of energy, and the discussion of exothermic versus endothermic, so knowing the difference. So question 1 says, draw a diagram of the energy story for the experiment in which a Cheeto is burned under a can of water. Be sure to clearly label all energy transfers and transformations you can think of. Identify the process as exothermic or endothermic. So let's draw our metal can of water, and let's draw our little food stand with our burning Cheeto. Okay. And first of all, we want to point out that the Cheeto has potential energy, and that is transformed into a few different things. So I'm just going to go off to the side, and a curly Q arrow equals transformation. And just a straight arrow is a transfer. So it's transformed into the thermal energy. It's also, some of it is transformed into radiation. And some is also transformed into sound energy. Okay, and then we've got this Cheeto thermal energy, which transfers to the water. So it becomes thermal energy in the water. Okay, and then some of that Cheeto's thermal energy escapes to the air. And some of it goes to the can itself. So I was going to say metal can thermal energy. So just to kind of show these in color, we've got a few different transformations we can point out, and then we've also got some different transfers. We hope that most of the thermal energy is going to the water, and yet there's definitely some that's escaping. So this process of the Cheeto burning, is that exo or endothermic? Well, if you have energy exiting the system in the process, oops, drew that arrow the wrong way. This is exothermic. So the Cheeto burning is definitely exothermic. Heat is exiting. And then just to point out the opposite, when the system is absorbing energy in a process, that's endothermic. All right, learning target 2 is all about specific heat capacity. So question 2 says you've got equal masses of water, which has a specific heat of 4.18 joules, are required to heat up 1 gram by 1 degree Celsius, and iron metal requires 0.45 joules to heat up 1 gram by 1 degree Celsius. They're both given 200 joules of heat energy. So which one is going to have the greatest temperature change? The iron metal. Why? The iron, has a lower specific heat than water. This means the same amount of energy applied to equal masses of the substances will result in a larger change in temperature for the iron, because less energy is required to change the temperature of 1 gram of iron by 1 degree Celsius. It only takes 0.45 joules versus 4.18 for water. So that's a big difference. It was kind of a wordier answer than I planned, but I wanted to make sure I was hitting everything. All right, so then you're expected to know how to calculate how much energy would be required to heat water, for example, through a certain temperature change. So when you see a change in temperature like this, and we've got a mass and we've got a substance, so we can look up its specific heat, the equation is Q equals MCAT. Mass times specific heat times the change in temperature. So the mass of the water is 250 grams. The specific heat for water, we can look on this little chart, 4.18 times, and then the temperature difference here, 22 up to 80. 80 minus 22 is 58 degrees Celsius. So 58 times 4.18 times 250. That's 60,610 joules. And just to show cancellation of units, grams cancels out, Celsius cancels out, so we're left with joules. Okay, next question. Which cup of water gets hotter? 450 joules of energy transferred to 100 grams of water, or 600 joules of energy transferred to 200 grams of water? Well, there's an equation we can use. Mass equals energy divided by specific heat times the change in temperature. Oops, that's not what I wanted. I want to switch these two. So change in temperature equals Q over mass times specific heat. So let's do it for the first cup of water. 450 joules is transferred to 100 grams of water, and we know the specific heat for water is 4.18 joules per gram degree Celsius. So this is going to give us units of Celsius. So I'm going to multiply the bottom first, 418. So 450 divided by 418, 1.08, and that would be degrees Celsius. So that's how much the temperature would change. Now let's talk about the change in temperature for the second cup. Q over M times C. So that would be 600 joules divided by mass is 100 grams times 4.18 joules per gram degrees Celsius equals. And then so we've got 600. Oh, sorry, the mass is 200 in this one. So the bottom is, we're actually dividing by a bigger number, so this is not even going to be close here. So 600 divided by 836. The temperature here will only change by 7.72 degrees Celsius. So which cup of water gets hotter? The first one. So even though it's less energy, it's only half the amount of water. So it changes more. So I'm showing my work with math. You could also do a good job explaining it just in words without math, just to give a heads up. So the first cup would get hotter. Less energy absorbed, but only half the mass compared to cup 2. So that makes sense. All right, a new material has been discovered. This could change the world. The specific heat of the new material has not been determined yet. You're the lucky scientist that gets to figure it out. You determine that it takes 2.4 joules to heat up 2 grams of the substance by 1 degree Celsius. What is the material's specific heat in joules per gram degree Celsius per 1 gram? Okay, so we can use the formula to find specific heat. It's Q divided by M times change in temperature. So it's 2.4 joules divided by 2 grams times 1 degree Celsius. So the answer would be 1.2 joules per grams degree Celsius. All right, and then the last learning target is being able to calculate how much energy is required or released for a phase change. So first one, how much energy is required to melt 25 grams of ice at 0 degrees Celsius? So we need to know which formula to use, and melting is the heat of fusion times moles. So what is the heat of fusion for water? Let's look it up. It is over here, 6,010. So 6,010 joules required to melt 1 mole. And we're melting 25 grams of H2O. So we have to get this into moles. So we've got to divide by the molar mass. Where did I get this number? I looked at the periodic table, and water is H2O. So I did H's molar mass and then times 2, and then oxygen's molar mass, and there's just 1, and I added that together, added equals this. And then now we multiply across the top and divide by the bottom to convert this into moles. 1.39 moles H2O. So going back here, times 1.39 moles. So 6,010 times 1.39 equals 8,354 joules. That's how much energy is required to melt that much water. Which makes sense because it's more than a mole. 1 mole is about 6,000 joules, and it's more than that. How much energy would need to be released in order for 2.5 moles of benzene at 80 degrees to condense from a gas to a liquid? So let's look at benzene. Its heat of vaporization is for condensation, so 30,700. Joules per mole times 2.5 moles. And this answer is going to be negative because we are releasing energy. So 30,700 times 2.5, releasing 76,750 in order for that many moles of benzene to condense. And this didn't include anything about heating or cooling curves, but that's definitely something you want to review just because it helps your understanding of how to do these calculations too. So there you are. Hopefully that's feeling like you have a pretty good grasp of the learning targets or are moving in that direction. Yay, yay.